and was the largest container ship ever when she was launched back in 2006. Of course, since then Maersk have bought out the Triple E class, which is slightly longer and wider, and other companies have bought out ships even bigger still. Her main engine weighs 2,300 tonnes and pumps out a whopping 109,000 horsepower. Now it's easy to compare that to a car, as they all publish the horsepower of their engines. For typical cars you're looking at about 100 horsepower, depending on the configuration you've chosen. At the extreme end you've got F1 cars which can be pushing 1,000 horsepower. It is a little trickier to compare that to an aircraft, as they use jet engines, which produce thrust instead of the mechanical horses that we use everywhere else. The maths is complex, but the best estimates I've found put typical 747 engines at around the 150,000 horsepower mark. So, for power it makes sense that the plane is the fastest, but the ship comes second, and she is still slower than the car, so there must be more to it than just the horses. With movement and things, another factor always makes an appearance: mass. It is in the energy formula, with kinetic energy being half mv squared, and it forms acceleration, force being mass times acceleration. So how can we add mass into this discussion? We can look at horsepower per tonne instead. For the plane, we can take the 747. They come in anywhere between 300 and 500 tonnes and are powered by 4 of those jet engines. A crude effort gives the power per tonne at, let's say, 1,200 horsepower per tonne. The car, we said, was around 100 horsepower typically, and you can assume a normal car weighs between 1 and 2 tonnes, and averaging that out gives you about 75 horsepower per tonne. Of course, with F1 cars, they're somewhat lighter and more powerful, so their figures are closer to the figures we got for the airliner. Now, the ship. Fairly obviously, she will weigh the most. A fully loaded Emma Maersk will tip the scales at, rounding off slightly, 200,000 tonnes. With her engine delivering 109,000 horsepower, we get her horsepower per tonne at around 0.5 horses per tonne. The vehicles are now starting to settle in the correct order. The plane is still out ahead, the car in second, and the ship is trailing a long way behind. But for the ship, from here on it only gets worse. Do you remember working out terminal velocity at school? It's when the force produced by an engine matches the resistance force from the medium the object is moving through. For example, you drop a ball, and it will fall faster than if you drop a feather. The wind resistance of the feather is much greater, so its velocity ends up being slower. The same applies with vehicles. The plane experiences air resistance, the car, a combination of air resistance and friction with the ground, but the ship is moving through water, a comparatively dense medium. This means she's experiencing the greatest force against her. The drag equation explains that drag is proportional to a cross-sectional area and the square of the speed. The cross-section we'll get from the breadth of the ship times its draft, which we can assume to be a constant for most ships. Of course, if you reduce the draft, like when there's no cargo on board, the ship will be able to go faster as there's less drag. Otherwise, drag is determined by the square of the speed. You double the speed, you quadruple the drag. You can, sort of, assume the force produced by the engine is constant. There are variations due to the water flow, but we can ignore those for now. All the while the engine produces more force than the resistance, the ship will accelerate. As she speeds up, the drag increases according to the square of the speed. Once the drag force matches the engine force, no more acceleration occurs. The ship has reached terminal velocity. For the Emma Maersk, this is around 25 knots, and that's typical for most large ships. For smaller ships, this is usually slower, and that's because their engines produce more power. But, crucially, their cross-section doesn't reduce in proportion to that change in engine power. There are ferries that do go significantly faster than normal ships. You'll have often heard them called fast cats. Fast cat is short for fast catamaran, and a catamaran is just a boat that has 2 hulls. Instead of a single box-shaped hull, the cat has 2 thin hulls. The separation between them produces the transverse stability that they need, and the buoyancy is just produced by the combined underwater volume of both hulls. Clearly there's less buoyancy, which means less carrying capacity, which is why they are usually only passenger ships. The key here is that you've drastically reduced the cross-section that produces the underwater drag. Reduce the drag, and you increase the theoretical maximum speed. Add on a few jet turbines and you've got yourself a ferry that's capable of speeds far higher than a typical ship. And what about small speedboats? Well, again, they reduce their cross-sectional area, allowing higher speeds. But rather than change the shape of the hull, they're designed to rise above the water instead of pushing through it. We call it planing. Above a certain speed, the water flow lifts the hull, reducing the cross-section, reducing the drag, and increasing the speed. Hydrofoils do a similar thing, except they have an underwater wing to produce the lift. At slow speeds, the whole hull creates resistance. As the speed increases, lift is generated, lifting most of the hull clear, reducing the cross-section, increasing the speed. It's the same theme for every watercraft that's capable of high speeds. It's all about reducing that cross-section, reducing the drag, and allowing a higher speed. If you've enjoyed today's discussion, be sure to subscribe for more videos like this every other Friday. Until next time, thank you for watching, and goodbye.